Good afternoon, everyone. I'm Santusht, and the research I'll be presenting today explores a question that feels almost paradoxical in today's world. Everything around us is accelerating: the way we travel on the ground, how quickly food arrives at our door, how information moves. But commercial aviation, one of the most technologically advanced industries on Earth, has barely changed in speed for decades. A flight that took 9 hours 20 years ago still takes 8 or 9 hours today, even on the most advanced aircraft like the Airbus A350. We've mastered efficiency, comfort, and safety, but not speed. And that gap is fascinating because it isn't a limitation of physics. We proved that we could go faster a long time ago. The Concorde crossed the Atlantic in 3 hours at Mach 2, crossing beyond the speed of sound. It was a symbol of what human engineering could achieve, but it never reached sustainable commercial success. And the reason had very little to do with the idea of supersonic flight itself, and far more to do with the world around it: high fuel burn, niche demand, and especially heavy restrictions on sonic booms over land. After the fatal Air France crash in 2000, a tragedy caused by runway debris, not supersonic flight, the fragile economics completely collapsed. By 2003, Concorde was gone. For me, that story isn't a dream, it's a signpost. It tells us that supersonic flight doesn't need a better dream, it needs a better plan. And to build that plan, we need data, structure, and we need tools that didn't exist in the Concorde era. That is where my research begins. Today, companies like Boom Aerospace are developing the next generation of supersonic aircraft that solve many of Concorde's engineering and design issues. But the biggest challenge now is beyond designing the aircraft itself, it's designing the network that surrounds it. The real question is, where in the world does supersonic flight actually make sense? This isn't something you can answer with a single formula or a simple map. It's a multidimensional optimization problem that requires understanding patterns across engineering, economics, and regulation. And this is exactly the type of problem machine learning is very good at uncovering. My research sets out to use machine learning to deepen our understanding of these patterns, evaluate route feasibility across the world, and identify routes that may not be obvious but could genuinely be viable for a future supersonic network. To tackle this, I built three things from scratch: a multi-factor route dataset, a pipeline of machine learning models, and an interactive prediction engine. The first major piece of work was constructing a dataset that actually reflects real-world constraints and combines the three factors together. This is the baseline of any machine learning project. For the engineering side, I used the online available HIMAC package as the starting point. HIMAC allowed me to compute great circle paths between airports, which are the basis for realistic routing. From these paths, I obtained great circle distance, subsonic estimated time, and supersonic estimated time. On top of that, I computed time saved hours as subsonic time minus supersonic time to assess the delta between flying subsonic and supersonic. I also encoded basic airport scale constraints, such as whether the airports are large international hubs with infrastructure compatible with large supersonic aircraft. Supersonic services historically targeted time-sensitive business and premium travelers, not mass leisure traffic. So for the economic side, I needed features that reflect market strength. For each margin and destination, I collected GDP per capita, population, and aircraft traffic level. From GDP per capita and population, I derived an economic power indicator, essentially a normalized version of GDP multiplied by population, scaled so that large, wealthy metropolitan areas ranked much higher than small, lower income markets. The idea is that high economic power correlates with higher volumes of travelers who can afford premium pricing and who value time savings, one that is prevalent in supersonic flight. Finally, I combined origin and destination economics into a demand score for the route, plus a qualitative bucket like medium, high, or ultra demand, which you will later see in my predictive engine. The regulatory side is dominated by sonic boom restrictions. Most countries still do not allow continuous supersonic flight over land due to large sonic booms that disrupt people, wildlife, and the environment. To capture this, supersonic jets need to fly over water. So I computed water percentage, the fraction of the great circle path that passes over water rather than land. The approach was to sample points along the great circle path at regular intervals, classify each point as land or sea using a global land sea mask, and then calculate the proportion of sample points over water. In the final data set, water percentage ranges from routes that are almost entirely over land to routes that are more than 90% over oceans or seas. Now, using these engineering, economic, and regulatory variables, I manually labeled each route as feasible or unfeasible for future supersonic operations. In the end, out of the 435 routes, 61 were labeled feasible and 374 were unfeasible. You can view my dataset through the QR code on this slide and also a quick snapshot of the Excel sheet. So now, with the training data complete, I went on to input this data into relevant machine learning models. My goal with this was to understand the main features that made a route feasible, find out the most feasible routes across the globe, and to build a predictive engine that could solve for any route worldwide. To achieve this, I used three main models. Firstly, a decision tree to extract fundamental decision rules. Secondly, an XGBoost classifier to achieve strong predictive performance and rank the most feasible routes. And lastly, SHAP values to interpret feature importance and check model behavior. I'll now go through each model and how they work in detail. The decision tree was my first model and my way of asking, if you force the algorithm to make a series of simple if-else decisions for each route, what does it learn about supersonic feasibility? The first split checks water percentage at a threshold of around 60%. Routes below that value are almost always classified as unfeasible. This reflects the reality that if you cannot fly mostly over water, sonic boom constraints essentially kill the route. For the routes that pass that filter, the next critical variable is time saved in hours. When time saved is relatively above 5.3 hours, the tree classifies the vast majority of cases as feasible. These are the routes where supersonic speed delivers a very strong value proposition. In the intermediate region, high water percentage but moderate time savings, the tree starts to use demand score and distance to decide. Routes with stronger demand and optimal distances tend to be classified feasible, others fall into unfeasible or borderline territory. Although the decision tree is not the best predictive model, it was very useful for extracting interpretable and visual rules that match physical and economic intuition. To get a more powerful classifier, I then trained an XGBoost model on the same feature set. XGBoost is well suited for tabular data with mixed feature types and can capture nonlinear interactions without overfitting too quickly. On the test set, XGBoost achieved about 97% accuracy, but the stronger metric is the ROC-AUC of 0.997, which basically means the model can distinguish feasible from unfeasible routes almost perfectly. 99.7% of the time, it gives the feasible route the higher score. That shows the structure of the dataset is strong and the model has learned the real patterns behind supersonic viability. Now, knowing that the model was strong, the next step was to ask which routes in the dataset rise to the top as the most feasible supersonic candidates. Some of the main routes included Singapore to Tokyo, Paris to Toronto, and the legacy New York to London route. What these routes share is very consistent. They all have high water percentage, strong time savings compared to subsonic travel, and robust economic power at both ends. They also sit within a distance band where a supersonic aircraft is expected to operate efficiently. Seeing routes like Singapore to Tokyo ranked so highly was particularly interesting to me because they're not the most discussed supersonic candidates in popular conversation. They were not even flown with the Concorde. Yet, the combination of geography and market strength in today's age makes them very compelling. Now, I needed a rigorous way to understand why the model was making predictions as it was. For this, I used SHAP. SHAP computes the marginal contribution of each feature by comparing predictions with and without that feature, averaged across many different combinations of other features. It assigns a value for each prediction, answering questions like, for this particular route, how much did water percentage push the model towards feasible or unfeasible? And did high economic power for the destination help tip this route into the feasible region? On the summary plot on the right, SHAP uses color to encode magnitude, red representing high feature values and blue representing low ones. And the horizontal position indicates whether a feature pushes a prediction towards feasibility or towards unfeasibility. High water percentage showed up immediately as the strongest positive driver. Routes that were mostly over water had SHAP values that pulled the prediction firmly towards feasible, while routes with low water percentage were pushed strongly in the opposite direction, as can be seen on the plot. Time saved in hours displayed similarly intuitive behavior. Large time savings consistently push predictions upwards, while small time savings pull them downward. Distance also appeared in a way that matched aircraft constraints. Longer routes within the Boom Overture's range, for example, contributed positively, but extremely short or extremely wrong routes nudged the prediction downward. Economic features added another layer of nuance. Routes connecting destination with high economic power and large population showed small and marginal but consistent positive SHAP contributions, especially in borderline cases. This means that strong economic centers can make marginally feasible routes more feasible and viable, while weaker markets tend to suppress feasibility even when the engineering conditions are feasible. To go a level deeper, I examined the SHAP explanations for individual routes instead of just the global trends. When I looked at high-scoring routes such as Singapore to Tokyo or JFK to Heathrow, the SHAP breakdowns matched exactly what one would expect from domain reasoning. High water percentage formed the backbone of the positive contribution, strong time saved that added significant weight, and robust economic demand from both economic hubs lifted the prediction even further. Seeing the signatures clearly in the SHAP output gave me confidence that the model wasn't operating as a black box. It was reasoning about the problem in ways that were consistent with physics, regulation, and market behavior. In other words, SHAP confirmed that the model's internal logic was aligned with reality and can be applied in real-world cases. Now I've trained these three models, and this is now putting the three components together. The decision tree gave me an interpretable first order rule set to look at, firstly. Secondly, XGBoost took the same feature space and learned a much more detailed decision boundary, which allowed it to classify routes very accurately and rank order them by feasibility. Lastly, SHAP closed the loop by verifying and showing route by route how each factor contributed to the outcome. So in one sentence, the decision tree is a very visual model. XGBoost gives us route feasibility and a top 20, and SHAP values tell us what exactly matters and how it works. From a research perspective, this combination of three models is very important. The decision tree is easy to explain to stakeholders and policymakers. It's very visual, easy to understand. XGBoost is what you would actually deploy instead of planning tool to understand what routes to fly. And SHAP is what you would use to justify that deployment and diagnose issues. The key insight across all three models is that supersonic viability is not dominated by a single factor. Engineering, economics, and regulation interact non-linearly, and route feasibility emerges from their combination, not their isolated values. So once the XGBoost model was performing reliably and the SHAP layer had confirmed that the model was reasoning in a way that aligned with real-world constraints, the next step was to make the system usable. I built an interactive radio application that essentially functions as a route prediction engine for both present day and future supersonic operation. The idea was to turn what was originally a research pipeline into a tool that someone could actually explore. In the interface, a user simply enters two airport codes, and the backend reconstructs every feature I described earlier. It computes the great circle path, estimates subsonic and supersonic times, interpolates the route to calculate water percentage, receives the relevant economic indicators, and assembles the future vector in exactly the same way the model was trained on. The output is a feasibility classification and a numerical feasibility score between 0 and 1. I also included a visualization of the path on a world map so users can immediately see geographical factors, particularly how much of the route lies over water, without needing to interpret tables of numbers. What makes the tool more interesting is that it doesn't need to stay fixed in today's landscape. The structure allows for scenario-based experimentation. For example, if low boom corridors become operational and effectively increase the permissible overland supersonic segments, the user can simulate higher water percentage values to see which new routes become viable. Similarly, adjusting GDP or economic power upward allows exploration of how future economic growth might shift the set of feasible routes. So now I'll do a quick demo of how it works, and you can also have fun with it using this QR code. Okay, so here we have the route feasibility explorer. And as you can see, I already have a route inputted, which I will now clear. So how this works is you can go onto the drop down and click any airport you would like to click. So I'll click London Heathrow as the origin airport, and I'll make, say, JFK as the destination airport. This is the most legacy route there is for supersonic flight. And this was also the route Concorde flew the most. So I click submit, and it shows me, it shows me this really nice map, which shows very easily shows the geographical features. So as mentioned earlier, you can see that the water percentage is really high, around 90%, which shows that it's a very feasible route. And below, you can scroll down and see some metrics that were used in this machine learning model. So the distance is around 6,000 km, which is in the range of supersonic flight. Water percentage is 92%. Time saved is a good amount, not quite long enough and not too short. And of course, demand tier is ultra, which gives it a very, very high score of 0.99 and hence being very feasible. But now let's look at a counter example from the world's longest route, for example, which is Singapore to JFK. And that will show us exactly what you would think, which is not feasible, because this is the world's longest flight with a distance that is out of range for supersonic flight. And as you can see on the map, it also barely passes over water. The over water percentage is 0.28. So you can experiment with this explorer. It's based both on trained data, and it can also work on untrained data, meaning there are thousands of routes at your fingertips over here. Now I'll switch back to the presentation. So to summarize, my research set out to answer where supersonic flight makes sense, rather than just whether supersonic aircraft are possible in a physics sense. I built a multi-factor data set, trained a decision tree, an XGBoost classifier, and used SHAP to interpret their behavior. The models consistently identified overwater routing, substantial time savings, and optimal distance as the core ingredients of feasibility, and highlighted concrete route candidates such as Singapore to Tokyo and JFK to London as strong prospects for future supersonic networks. The interactive prediction engine then turned those insights into a usable tool capable of evaluating any global route under different scenarios. Now, there are a lot of future implications this project can have. For example, currently the features are limited to just a few engineering, economic, and regulatory features, but it can also be extended to include fuel efficiency, which is a really big thing with supersonic flight as it's very fuel hungry. And it can also be more accurate with the regulation, as different countries have different supersonic regulation. And if the model can adapt to that, that will make it even more accurate and allow for more routes to be shown that are not being shown right now. And last but not least, of course, I used 435 routes, which can definitely be expanded. In machine learning, the saying goes, the more data you have, the better it is. Um, and of course, with more data, we could look at more route types over land, over water, a mixture, and also explore the potential of detours of routes and one-stops that still work against subsonic flight. So broadly, the conclusion is that supersonic flight is no longer limited by aerodynamics alone. It is an optimization problem across engineering, econs, and regulation. And that's exactly the kind of problem I use machine learning to formalize and solve. I'm excited by the idea that if we do this planning more in depth, a future generation might see a return of commercial supersonic travel that is sustainable, economically grounded, and much more robust than Concorde ever was. I'd like to thank my mentors, Dr. Hannah Rana from Harvard and Mr. Arun Kumar from Cambridge, for all their support and guidance. Their rigorous lessons and teaching hours really helped me in my research. Thank you.
Thank you very much for presenting this excellent piece of work, Santusht.